Okay, welcome back. In the last example, what we did is we took a horrible looking matrix filled with fractions and we were asked to take its determinant, and what we did instead of calculating it in a straightforward way using a secret method was we explored taking the fractions out, factoring a fraction out of each row. So factoring 1 over 6 out of row 1, factoring 1 out of 2 out of row 2, and factoring 1 over 3 out of row 3. And it ended up not saving us anything for this question. At the top right, I show you the calculation to use the secret method to take the determinant of the original matrix without factoring anything out. It's actually faster. It's a little bit less work. But that's particular to this example. There's so many zeros in the matrix that it canceled out a lot of the terms that would have had non-common denominators. So we would have had 18, like depending on what those numbers are, we would have potentially not had common denominators across them if we replace those zeros with other numbers, like especially whole numbers, like 6s and 7s and stuff. So in general, if you can factor out, it saves you. But there are some examples like this one where it isn't necessarily beneficial to factor out before you take a determinant, just sometimes. So remember that property that we had as one of our early shortcuts for taking determinants, where one of the rows in the matrix is a scalar multiple of another row in the matrix. So let's say row 1 is 3 times row 4, or the same thing for a column. If column 5 is 8 times column 2. If you ever see something like that in a matrix, it's a guarantee that the determinant is going to be 0. They're hard to find. So you look at a matrix like this and you stare at it a long time. Can you see one row or one column as a multiple of another row or another column? There's a pi in there. I don't see any of the pi, so we can just ignore that row and that column. But let's see. So 6 to 8 has a different relationship than 6 to 1. I don't see any duplicates. But look at this. If we take this row and this row and compare them, row 2, or not column 2 and column 3, compare those two. What is column 2 multiplied by 3? It's the third column. So those two columns are only different from each other. I gotta check all of them before I proceed with this statement. They're only different from each other by a multiplication by 3. So we can tell that the determinant is going to be 0. Yeah, okay, it was that one. Good. Hopefully it wasn't a second one, a second flaw in the matrix. So this shortcut is still there, and if you see it, it's still the fastest way to defeat the determinant, or to find the determinant is 0. Okay, let's look at another type of experiment. The experiment I want to look at is what happens if I take a matrix and I do a different row operation. So we looked at multiplying a row by a constant or dividing a row by a constant. Now what we'll look at is exchanging the order of 2 rows. And we'll extend that to exchanging the order of 2 columns, which, by the way, when you're doing elementary row operations to row reduce matrix, don't touch column operations. Column operations are only for determinants, at least as far as this course is concerned. Okay, so here's our starting matrix A, and then we're going to perform some manipulations on it. The first manipulation is to interchange row 1, row 2, but let's find the determinant of A first so we know we have a valid comparison. Determinant of A is down products minus up products, 1 times 4 minus 3 times 2, 4 minus 6, so negative 2. Now let's see what happens if we swap row 1 and row 2. So the determinant of B is equal to 3 times 2, down product minus up product, 1 times 4, 6 minus 4, which is positive 2. Okay, let's look at a column. What if I interchange column 1 and column 2? So I just swap this way. What's going to happen? Determinant of C is 2 times 3 minus 4 times 1. So 6 minus 4, which is 2 again. So changing a row and changing a column both gave us the negative of what we started with. And then what happens if we do two operations? What if we interchange row 1 with row 2 and then we interchange column 1 with column 2? So don't do them both at the same time, you'll confuse yourself. Row 1, row 2, swap those, and then from that result, so from B, now swap those two columns. So we're really going from B to D by swapping some columns, or from C to D by swapping the rows. Now let's take the determinant of D. Determinant of D is down products minus up products. So 4 minus 6, which is negative 2. We haven't done nearly enough experimentation, even with a 2x2 matrix, to be confident about what this experiment, what we'll claim about this experiment revealing, but it's okay. Oh, 3x3, what happens if we do a swap here? So here's our original matrix A. Our determinant of A is going to be down products minus up products. So our down products, we have 1 plus 0 plus 0 minus our up products. Our product is 3 plus 0 plus 0. So 1 minus 3 is negative 2. Probably wondering, how do you do that? How do you do that without writing them? I'll show you a shortcut to the secret method. What is your down products? Your down product says here's one of them. When you make the copy of the matrix, this is going to be another one. This one is going to be in the copy over here. So I'll just think of this as like a portal that teleports me back to here, back to this point. And then I have one more down product that's going to be this one, that one, that. And my up products, I'm going to have this up product, 1 times 1 times 3. I'm going to have this one, 0 times 2 times 1. And I'm going to have 1 times 0 times 1. And have those as my up product. So that's imagining what would happen if I made a copy side by side. Okay, now the determinant of B, when we swap two rows together, what we expect is, based on this experiment, we swap two rows and the determinant got multiplied by minus 1. Change the sign of the determinant. What I would expect is I would expect to get positive 2 from this determinant. I'm going to do this one the long way. Or not the long way, not cofactors, but like writing out the whole thing. 0, 1, 0, 1, 2, 3, 1, 1, 1. Because I think every time I do an operation like that in class, like the down products minus the up products without actually drawing the pieces, people will start getting freaked out. Don't do that. No, no, no. It was good before. Why did you change it? So I won't change it. So down products minus up products. So our down products, we have a 0, we have a 3, they're just in different order. And we have a 0. And now my up products, 1 times 2 times 0, 1 times 3 times 0, and 1 times 1 times 1. So 3 minus 1, we get 2, which is the negative of the determinant of A. And then if we do a swap of, instead, row 1 to row 3. So we go back to the original matrix and swap row 1 and row 3. 1, 1, 1, 1, 1, 1, 1, 2, 3, 1, 2, 3, 0, 1, 0, 0, 1, 0. Hide the last column. And we're going to get down minus up, which is so the first down product is 0, second down product is 0, third down product is 1 minus the up products, 0, 3, 0. So we get 1 minus 3 . 1, 1, 1, 1, 2, 3. Oh, wait a second. Down products. Minus 2. Oh, something's wrong. Hold on. So 0, 0, 1. That part's so far so good. Maybe no, I wouldn't have messed up that. Oh, I see what happened. No. Okay. This is from B, starting from B, not starting back from A. Starting from B. So we get negative 2, which is negative 1 times negative 1 times the determinant of A. So what happened here was we first swapped row 1 with row 2. That introduced a negative sign to the determinant. Then we swapped, from that new matrix, we swapped row 1 with row 3, and that picked up another negative 1. And we ended up with the original determinant back. So the result of this experiment is indicating that every time we swap two rows, the determinant picks up a minus sign. And if we do it multiple times, it's going to pick up multiple minus signs for however many times we do that type of row swap operation. So here's a theorem that formally states this. I'll get my camera focused to reset. Formally states this property. It says that if we have a matrix B that is obtained from a matrix A by performing row swaps, by interchanging any two rows or any two columns, and I didn't do an example proving it, but you can do it on your own if you want, then what will happen is that the determinant of that new matrix will be equal to the negative of the determinant of the original matrix. So an example that we would use this property for is shown here. This matrix is a 4 by 4. It does have a nice row that we could do a cofactor expansion along. We could do a cofactor expansion along row 4 or along column 1. Those would be relatively simple calculations, but not as simple as making this a triangular matrix. So we can make this into a triangular matrix if we swap row 2 and row 3. So notice what will happen if we do that. So determinant of A is equal to negative 1 times the determinant of, so that negative 1 comes from the row swap we're about to do. So I'll call it the cost of swapping two rows. This picks up a negative sign for the determinant. We have 2, 5, 9, negative 7, 0, 5, 8, 1, 0, 0, 3, 11, 0, 0, 0, negative 1. And what we did is we swapped row 2 with row 3. Okay, now this is a triangular matrix, so we can use a triangular matrix. It's upper triangular. You use the shortcut. So we have -1 multiplied by the product along the diagonal, 2 times 5 times 3 times -1. So we're going to get 30. And that's much faster than doing cofactor expansion. Here's another one. This is another 4x4 matrix. There's lots of different rows or columns we could do a cofactor expansion along. So we do have relatively good options for doing this calculation, but none are as good as turning this into a triangular matrix. So goal, convert to triangular matrix. So determinant of A is equal to, let's start with getting that row 3 where row 1 is. So that'll cost us a negative sign. So I'm just going to row 1 swapping with row 3. That's this. That's that minus sign. And it's important to write down your steps, indicate what you did as part of your accounting process. So 1, 0, 1, 1. Row 2 stays the same. We didn't do a row swap there. 0, 1, 1, 2, 0, 0, 2, 1. Okay, now I want to do a row swap between row 2 and row 3. So that additional minus sign, that is the cost of row 2 swapped with row 3. One, 0, 1, 1. 0, 1, 1, 2, 0, 0, 0, 3, 0, 0, 2, 1. And we're almost there. We almost have a triangular matrix, upper triangular, and now I'm going to swap row 3 and row 4. -1 times -1 times -1 times the determinant of, so that last -1 gets picked up, row 3 swapping with row 4. One, 0, 1, 1, 0, 1, 1, 2, 0, 0, 2, 1, 0, 0, 0, 3. Now it's upper triangular. So we use a shortcut. So we'll get -1 times -1 times -1 multiplied by 1 times 1 times 2 times 3. So we'll get negative, from 3 negatives multiplied by together, times 6. So -6 will be the answer. And we'll continue in the next video. It's close to 20 minutes.